Welcome to the APCTP Colloquium this week. So today we are very happy to invite Norman Yao, Professor Norman Yao at Harvard, who will talk about his the very interesting time crystal. So before we go on to the talk, let me introduce briefly about Norman's career. So he finished his PhD at Harvard University under the revision of Professor Mikhail Lukin in 2014, and then and afterwards he started the postdoc position at University of California as a Miller Institute of Basic Research and Scientific Fellow, and then 3 years later, in 2017, he became an assistant professor of physics in the same University of California at Berkeley, and became associate professor in 2020. And as far as I understand, this year he moved to Harvard University as a professor in physics. So he had won many prestigious awards and honors, such as Deborah Jean Award for Outstanding Doctoral Thesis Researching AMO Physics, Georgie Valley Junior Prize of the American Physical Society, Breakthrough Foundation New Horizon Prize, and Presidential Early Career Award for Science and Engineers. So Norman has so many achievements that it's difficult for me to summarize what he have done in very short time, but very naively, very roughly speaking, as to my understanding, he have been transferring some very fancy, abstract, interesting theoretical concept into a realistic platform, such as quantum information scrambling using quantum simulators, topological phases, non-equivalent dynamics such as time crystals, and many-body localization, and so on. So today, we're lucky that he will be presenting about perhaps the most known result of his work, which is time crystals. So Norman, the floor is yours.
Excellent. Thank you so much, Kisiot, and also thank you, Ryu, for such a nice introduction, for the kind invitation to allow me to talk about some of my group's recent work. Yeah, I think maybe I didn't hear the part precisely about Lenny Susskind, but I might have made the same mistake. There was recently a time change, and in my calendar, I also basically had it an hour later because it was because of the time change. But I'm glad I checked just at the right moment. So I'm glad I'm here with you all. Thank you so much. Okay, so I'm really excited to tell you a little bit about some of my group's recent work in the last several years, focused on the question of time translation symmetry breaking. And in particular, I'll try very hard to answer the question, what is a time crystal? And I encourage you, please, I think the goal of this talk is really, I was told the audience is tremendously broad. So the goal of the talk is really to try to introduce some very, very general ideas. And so please feel free to interrupt me with questions at any time during the talk. All right, so I'll be talking very broadly about trying to introduce the flavor of the question that we try to ask, and then a little bit more towards the technical piece will be based on some recent work from myself together with Chetan Nayak, Leon Balance, and Mike Zalatel. And then towards the end, with some work again with Mike Z, and also Francisco Machado and Trintao, who are students of mine. Good. So let me start with a very, very quick roadmap for where I'm going to go. So I will try in the introduction to be very careful about defining the nature of the question, and we'll sort of revise the nature of the question very slowly as we go through the talk. And I want to emphasize that there are many, many contexts where the question is answerable in sort of a simple way. And so in that sense, I want to be very careful about defining when the question is interesting and hard to answer. Then we'll talk about time crystals, and we'll try to contextualize the modern results in time crystals within some very, very old literature on dynamical systems. And in particular, I'll describe in a little bit of detail the case of a very simple system called the logistic map. Then I'll turn to perhaps the most modern setting that people are thinking about time crystals, which are essentially in closed, periodically driven many-body systems. And here, I'll try to emphasize that at some deep level, the question about the stability of time crystals is really a question about the notion of ergodicity and how to avoid ergodicity in these types of systems. I'll, at that point, introduce what I think is a very, very simple sentence. If it's the only sentence you take away from the talk, it's sufficient, which is that as a general setting, wherever there is ergodicity breaking, there should be essentially some version of time crystals. And in that context, I'll talk a little bit about the case of Floquet-Langevin dynamics. And finally, I'll end with a little bit of a broader outlook on where I think there are some interesting open questions for the field. So let me start. So I know many of you, some of you are tremendous experts on this topic, but let me just try to get all of the students and postdocs and everyone on the same page in terms of language. So at the end of the day, I want to introduce sort of a formal notion of time crystals as essentially a type of phase of matter, although in an intrinsically non-equilibrium setting. So I want to be specific in terms of talking about phases of matter in the first place. So phases of matter, you often think about phases of matter in the context of phase diagrams. So here is a classic phase diagram that you have all seen or that you experience in your day-to-day life. It's the pressure, temperature phase diagram of water. And we oftentimes think of phases of matter defined by the fact that there are transitions between them. So for example, there's a phase transition if you cross this line from solid to gas. There's a phase transition if you cross this line from liquid to gas. But it turns out that oftentimes there is also the notion, if in this plot, you can see that actually there is a way to go, for example, from the liquid to the gas phase without necessarily going through a phase transition at all. And to understand this type of a concept, it turns out that it's extremely important to think about the nature of the symmetries of the problem, and that ultimately connects to sort of an underlying definition for phases of matter that I want us to think about. In particular, if we think a little bit more broadly about the picture that I've just drawn, I claim the following, that in general, you can imagine that there are two phases of a system of many, many particles. And you can imagine putting these two phases again on a phase diagram, just like we were seeing in the previous slide. I claim the following. I claim that in principle, if you have a solid and a gas phase, no matter how you go from the solid to the gas phase, no matter what path you take in parameter space, you have to go through a phase transition. But generically, for a liquid and a gas phase, sometimes if you take a particular path in PT space, you will go through a phase transition. But other times, there will exist a path that goes around without going through the phase transition. And it turns out, at its core, the difference between these two pictures and the notion of a liquid-gas transition or a solid-gas transition and the phases of matter that they represent is fundamentally based on the notion of symmetry. Okay. So let me be very specific about what I mean by symmetry. Throughout the talk, I will imagine that we're describing a many-body system and that we're thinking about the static and dynamic properties of that system being governed essentially by some set of equations of motion. You can think about them as Lagrangians, but I'll be more comfortable thinking about them essentially as a Hamiltonian. And when we talk about symmetry, we're saying something extremely simple. We mean that there exists some transformation that keeps these equations of motion, aka the Hamiltonian, exactly the same. And it turns out this notion of there being, for example, a state like a solid state corresponds to the fact that the state of the system, oftentimes upon cooling it down, for example, lowering the temperature of the system, can exhibit a state that breaks the symmetry that corresponds to the Hamiltonian symmetry in the first place. So it can be that at low temperatures, there is a notion of ordering. A solid is an example of this type of ordering, which breaks the spatial translation symmetry of the Hamiltonian in the first place. And it turns out, upon breaking the symmetry, you can measure this notion of symmetry breaking via a so-called local order parameter. In the case of the solid, it's the density of the particles as a function of space. So the key concept that I want to introduce here, just to make sure that everyone's on the same page, it's very simple, is that really when we talk about phases of matter, we're thinking about the spontaneous breaking of some symmetry. In this particular example of thinking about solids and gases, we're thinking about the spontaneous breaking of a translation symmetry. And for a time crystal, we'll be thinking about the translation symmetry breaking of a time translation symmetry. Okay. So let's go back almost precisely 10 years
Simple
ago.
question.
Yes, please.
Yeah, in the previous page, so in the right phase diagram, liquid gas transition, if as you mentioned, if I cross some detour route, there will be no phase transition crossover. What is the physical picture? Can you draw some how it changes?
Exactly. Good. So let me make a very quick statement. Exactly. So you should think about, for example, a simple way is to think about the order parameter of the system. Let's think about, for example, saying something like, how, homogeneous the system is, and how homogeneous the system is, we can think about essentially as an order parameter that corresponds to the solid being very inhomogeneous. It has specific locations for atoms in space, and the gas would be an example of a very homogeneous thing. And the key difference is that whenever you go from a solid to a gas, you essentially go from the order parameter being 0, always jumping to some finite value. But the liquid to gas transition, you can think about essentially as being the order parameter for the gas having some finite value on this side. And as you go across, it can jump from one finite value to a different finite value, or you can imagine it going smoothly from one finite value becoming smaller, and ultimately ending up at the other value. But if you know that the order parameter is 0, identically 0, for example, then of course, when you go from 0 to sort of some finite number, you always go through a jump and you always go through a transition. So in some sense, you can have a transition where the order parameter jumps between two finite values, but whenever that's the case, there's always a path and parameter space that allows you to go continuously. But if you move from 0 to a finite number, you always have a jump. Is that clear?
So can you mention some criteria when such path exists and when? So can you have some mathematical criteria, left figure and right figure, in which case there is no such path doesn't exist and exists when?
Yeah. I think that mathematical rigorous statement is exactly, I think, in terms of the order parameter. So if the liquid phase is defined by a finite expectation value for a local order parameter, and the gas phase, for example, is defined by a different finite value for that order parameter, if it's two finite values, then you do not have to have a jump between them. You can always go from one finite value to the other. But here, the mathematical statement that there must be a phase transition is that, for example, depending on whether or not you define the solid or the gas as being the ordered one, you can have basically the order parameter being strictly 0 in one of the phases. And when it's strictly 0, when the expectation value is strictly 0, then in order for it to go from 0 to a finite value, you always have to go through a discontinuity. And that means that you always have to go through a phase transition.
Okay, yeah, thank you.
Yep, very good. Super good question. So it's really very simple. At the end of the day, phases of matter, at least in the context of condensed matter physics, we think about really with respect to symmetries. You take the equations of motion, in this case described by a Hamiltonian, you ask what symmetries are there? And then when you think about defining a phase of matter in a kind of classic Landau-Ginzburg theory, it's really a statement that the state of the system can exhibit a lower symmetry breaking, than the parent Hamiltonian. And the example of solids and gases is an example of a symmetry of translation in space. And the example of a time crystal that people were thinking about is an example of a symmetry in time. So the original idea was in a set of very, very nice papers by Frank Wilczek and Al Shapiro and Frank Wilczek. And they were asking essentially the same question about translation symmetry, but with respect to a time translation symmetry. So what do I mean when I say, for example, that a Hamiltonian or a set of equations of motion exhibit a time translation symmetry? The simplest notion of that is, in fact, that the Hamiltonian is just time independent. If the Hamiltonian does not depend on time, then for every instant in time, the Hamiltonian is the same. So there is an arbitrary translation in time by any continuous small amount that leads the equations of motions to be unchanged. If you want the state of the system, for example, let's imagine we're thinking about the quantum ground state of the system, to spontaneously break the symmetry of the Hamiltonian, what does that mean? It simply means that it would be nice if there was, for example, some sort of a local observable such that despite the fact that the Hamiltonian is time independent, the local observable, for example, exhibits some non-trivial time dependence. Okay? But it turns out it's very, very trivial to prove, just looking at Schrodinger's equation, that if you, for example, think about the ground state and you plug in for the dynamics of the ground state as a function of time, it simply picks up a phase. So you can immediately show that for the function on the left over here, there cannot be any non-trivial time dependence. It has to be a constant. But Wilczek and Al-Shapir and Wilczek were thinking about a slightly more complicated scenario. They said, well, let's not take just a one-point correlation function. Let's imagine an autocorrelation function or a two-point correlation function. So let's imagine O of 0, O of xt. And here, it's much less easy to prove trivially that you cannot have a non-trivial time dependence. And if it were true that there was some non-trivial time dependence for this type of an order parameter, that would absolutely represent a case of spontaneous breaking of the time translation symmetry of the Hamiltonian. And the question, of course, was not just asked for ground states, but also for thermal states e to the minus beta h. It turns out that, I think many of you will be looking at this and thinking to yourself, well, this clearly doesn't, would be surprising if this were possible, because in some sense it says that the equations of motion are unchanged, but if there is a local observable that is oscillating in time in some way, then essentially it has a very weird feeling from a physics perspective of being something similar to a perpetual motion machine, right? The idea would be that you have the governing equations of motion for the system do not change in time, but there is some observable in the state of the system that is changing in time. So I should be able to make some engine out of that observable such that because of the oscillation in time, I should be able to get some work out of that system, despite the fact that because the Hamiltonian is not being changed, I'm not really putting work into the system. So I think for many people, Pat Bruno, Noziers, a lot of people at the time when the idea came out, people were sort of skeptical that this could be possible. And it turns out that, this skepticism, I think at some level, but motivated by a very beautiful question, Frank and others, ultimately culminated in a simple no-go theorem from Haruki Watanabe and Masaki Oshikawa, where they essentially proved that non-trivial time dependence of this form for either ground states or thermal states was not really possible for a purely time-independent Hamiltonian. But then people started to think a little bit more, and people started to think that, well, maybe taking this fundamentally equilibrium setting where the Hamiltonian itself is purely time independent is a little bit too restrictive. And so people broadened the question. This changes the nature of the question in the first place. People started thinking about the question in a little bit of a different context, and they started to ask the same question about the breaking of a time translation symmetry, but they started to think about it in a non-equilibrium setting. And perhaps the simplest way to take any physical many-body system out of equilibrium is for the equations of motion to be time-dependent, but to be time-dependent in a very, very basic way for them to return to themselves via periodic driving. Okay? So the original question that Frank and company were asking was a beautiful question, but they were thinking about it for what's called a continuous time translation symmetry, a Hamiltonian that's fundamentally independent of time. It was proven that at least in that context, it's not really possible to get spontaneous breaking of that symmetry. So people started to think in a non-equilibrium context. And in the non-equilibrium context, people started to think about, the first thing people looked at was the periodically driven case where the Hamiltonian here is time dependent, but it's time dependent in a very simple way. It returns back to itself every driving period, capital T. Okay, so the context of the question is slightly different. But it turns out when you look at this and you think about this, you might say, okay, if I think about a lattice, for example,
Or
yeah, please, Rio.
Yeah, so I think in the Watanabe and Oshikawa paper, they were considering a short-range interacting system, and therefore, at least in principle, if you have long-range interaction, it sounds like in principle you can get this time crystal, at least in principle, even in equilibrium.
A very
So
subtle question. It's a very, very subtle question. That's right. So, okay, so let's be very careful about this. So that's right. Watanabe and Oshikawa consider the situation with short-range interactions, and it's possible to consider a situation with long-range interactions or ultra-long range. So let's be very careful. So let's imagine that we have, a scenario where we have degrees of freedom that interact with each other. The simplest generalization is via a power law, Coulomb or dipole-dipole or van der Waals, some power law interaction that decays as 1 over the distance between the particles to some power alpha. Okay?
Right.
So there's one scenario where, for example, alpha itself is essentially, it is long range in the sense that there's a power law, but the eigenspectrum of the many-body system is extensive. So if you have the power law falling off faster than the dimension of the system, it's what we call sort of, power law, but essentially short range from the perspective of extensivity. Okay.
Right.
But there's another situation which people have considered, I think Vlad Kozary and others considered, which is the ultra long range case where, for example, you think all to all coupled. So you take the power law 1 over r to the alpha and you take alpha towards 0. In that limit, it's true. You get essentially a mean field model that describes 1 degree of freedom. It's sort of almost like a large spin degree of freedom. And in that case, all of the things that I'm talking about sort of break down. There's no thermodynamic limit in the way that we like to think about sort of with respect to statistical mechanics, but it's certainly true that if you allow yourself a system that is all-to-all interactions, you can get continuous time translation symmetry breaking. So I think what Rio said is very, very good.
The question that I wanted to ask was that, I think you mentioned that the intuition behind why time crystal order is usually not possible is because there's usually dissipation, and that will make the system go to a stationary state. And in order to have this time crystalline order, probably you need some drive such that you keep on driving the system to have time periodicity. That's kind of my intuition. And so in the long range interacting all-to-all coupled system, am I understanding intuitively correct that in that all-to-all spin system where the effective degrees of freedom becomes very few, then essentially you can have a precision of a macroscopic spin that can be regarded as the time crystal? Where is the intuition, do you think, is
I think that intuition is actually perfect, but let me restate it a little bit, just to be a little bit careful, but I think it's perfect basically. So what Ryu said is exactly correct. So in the many-body system, Ryu emphasized that there's some notion of dissipation. And I want to be very careful for people who haven't thought about this before, because when you think dissipation, oftentimes if you think about many-body physics classes that you've taken, dissipation, you oftentimes think of it in terms of a master equation or a Limblad equation or a Langevin equation, some equation that essentially has some notion of dissipation in the actual dynamics of the system. But what Ryu is saying is something slightly different. So remember, the context here is a closed system. It is not coupled to a bath. So strictly speaking, you are not thinking about a dissipative system as in there's a system coupled to an environment. I think what Rio is saying, which I totally agree with, is that essentially there's thermalization. That what happens in these systems is that thermalization, you can kind of think about as, many of the degrees of freedom acting as a bath for little subsets of the system. And when you have thermalization, in general, you go to, again, I wouldn't use exactly necessarily the word of a steady state because that makes me think of a master equation, but really you go to some equilibrium state. And the assumption of ergodicity is that that equilibrium state is basically unique. And in that sense, once you have a unique equilibrium state, you have no more symmetry breaking, period. Because when you have symmetry breaking, you need to somehow remember which orbit of the symmetry you're in. So if you go to one equilibrium state, then you cannot remember that. And then Ryu is also exactly correct that when you have one macroscopic object, forget ergodicity. Ergodicity is a statement about basically essentially a many particle system acting as a bath for itself. And so if you have all-to-all coupling that essentially makes your spins behave like one big spin, it's essentially just a needle, and that needle can precess, and the precession of that needle, of course, can look at break spontaneous symmetry. But that's very, very different spiritually than having a many particle system where there is a well-defined thermodynamic limit as you take n to infinity.
Yeah, thank you. Yeah.
Good. So the question is different. So after 2015, the question that was being asked was just fundamentally different than the question that Frank originally asked. And now it was a question about the nature of time translation symmetry breaking in periodically driven systems. Okay. So again, if you think about in the simplest way, representing, for example, this symmetry on sort of an axis, you would say that if the Hamiltonian is time independent, then every point along this black line has the same Hamiltonian. So there is a time translation symmetry that's continuous. But when you have a periodically driven system, you've broken that symmetry. You've broken the symmetry that Frank Wilczek originally envisioned, because now the Hamiltonian only returns back to itself at time period t, at time period 2t, 3t, etc. And these are typically called the stroboscopic times for this periodically driven system. So you might ask, okay, doesn't that mean that thinking about this with respect to the original setting, that the Hamiltonian itself being periodically driven, that the symmetry is already basically broken? It turns out that's true, that the continuous symmetry is broken. But now the question about the spontaneous breaking of the time translation symmetry refers to a question about the breaking of a discrete time translation symmetry. Okay, so you've now changed the question about continuous symmetry breaking to discrete symmetry breaking. And again, I know that many folks, for you, for example, will be super familiar with these concepts, but let me just, for the broader audience, introduce it via a very simple analogy to space. So, you're very, very used to thinking about discrete spatial symmetries in the context of spatial translation symmetry. So you could, for example, have, a system of atoms that are totally translation invariant. And let's say the Coulomb interaction between those atoms leads to a lattice in a material that, for example, is this very famous Kagame lattice. Okay? So this lattice of atoms, thinking about that, already breaks the spatial translation symmetry, the continuous spatial translation symmetry that we normally think exists for physics. But you can ask, on top of this, if I put a bunch of interacting electrons, what can they do? Well, they can certainly be in a state where the density of electrons is totally uniform on the Kagame lattice, or they can form a density wave pattern. So this would precisely be called a charge density wave, where the electrons, for example, form some additional structure and they break the translation symmetry, the already discretized spatial translation symmetry of the underlying atom. So usually, just from the perspective of nomenclature, if you have a continuous spatial translation symmetry and your atoms break that translation symmetry to form the black dots, that we call the crystal. If you have a degree of freedom like an electron living on top of an already discretely broken spatial translation symmetry, but the electrons further break that discrete symmetry group into a smaller group, clearly this is a smaller group, we typically call that a density wave pattern. So in some very truthful and honest way, the word time crystal is not really a very accurate name for the thing that people are studying these days. Really, people are studying an additional discretized breaking of an already discrete time translation symmetry. So really, in the analogy to space, we should be calling these objects time density waves and not time crystals. Okay. So let's just go back, for example, to the setting for today's talk one more time. The idea is that, in a discretely, if you have a lattice in space, you can have a density pattern that bakes that already discretized spatial translation symmetry. And if you have the same thing in time, you can imagine that the definition of a time crystal is then a system who has an observable that only comes back to itself, for example, every 2 driving periods, or every 3 driving periods, or every 4 driving periods. This would correspond to a subharmonic response on top of the already periodized Hamiltonian. So for most of this talk, we'll focus on a very specific example of, subharmonicity, and that's the notion of period doubling. We'll imagine that observables, for example, of this time crystal come back to themselves every 2 driving period instead of every single period. Okay. So I just want to make sure, is the setting, setting changed a little bit since we introduced it, but is the setting clear for the question that's being asked? Great. So the question now.
Again, maybe somewhat stupid. Is that if I consider completely continuum system, so is there some rigorous, translation symmetry breaking can occur, even without lattice, block theorem. So am I correct?
Yes, absolutely. Spatial translation symmetry can absolutely occur, even, for a totally continuous translation. That's what a crystal is. So
then what's the difference in space translation symmetry breaking and time translation symmetry?
Space and time are just different. Yeah, that's a good point. This is essentially sort of, related to, all of the things that we know about, okay, maybe let me say it this way. So, when we learn about special relativity, or when I learn about special relativity, we try to put time and space on the same footing. But at least in the context of symmetry breaking, time and space are very different. In the context of, the second law of thermodynamics or entropy, time and space are very different. There's some notion that you can move forwards and backwards in space, but that there is some arrow of time. So I think that it's true, that time and spatial translation symmetry are fundamentally different. That in this case, you can have the breaking of a continuous spatial translation symmetry, but a la Watanabe and Oshikawa, you cannot have, at least for a short range interacting system of many particles, you cannot have time translation breaking of a continuous symmetry.
I see. Okay, let me consider more. Thank you.
Yeah, so a related question perhaps, but like how much of this, like the Watanabe and Oshikawa's proof like relates to the Mermin-Wagner's theorem, for example, in space, like in the space, whether you can have order in space or not usually depends on, the large fluctuation that comes from the Goldstone mode, whether that will kill or not. Is there any similar picture in this, in the time
I would say they're spiritually related, but there is no relationship. Formally, there's no relationship. So let's think about why for a second. So Mermin-Wagner is a statement about the stability of fluctuations. It tells you about whether or not you can have a very, very good question, actually a really good question for you. It tells you about whether or not you can have spontaneous symmetry breaking, but really the way to think about it is a question as to whether or not you can have it at finite temperatures. So for example, the classic example that everyone thinks about is, one-dimensional magnetism. And the usual answer in this case is that for a one-dimensional magnet, essentially, if you have a domain wall, the entropy associated with that domain wall basically looks like T log L or T log N, basically. And that, because you have a log divergence in N as you take the thermodynamic limit, will always overcompensate for whatever the order 1 energy of a domain wall cost is, right? That's how we think about Mermin-Wagner. But, the answer in Watanabe Oshikawa is unrelated to that type of fluctuation or that type of sort of entropic argument at all. It's just a statement about calculating basically how the observables change in time and showing that there cannot be a time dependence.
There's no like fluctuation involved in their proof.
Yeah, you don't think about thermal fluctuations in that way. Or thermal fluctuations, for example, are not the thing that breaks it.
I see. Okay, maybe then the related question: is it that you cannot have time crystals in classical settings?
No, I don't believe that. So it's another super good question. So I hope I will convince you all and at least explain it very clearly. There is a question. I believe it's true that time crystals were originally maybe found or studied in the context of quantum systems and driven quantum systems. And you can ask yourself, what exactly is the key? So is it true that basically, what is the essence? Is it true that basically the order associated with time translation symmetry requires quantum mechanics, or is it something else that was special about the quantum mechanical setting? And my claim is that it was something else. And the something else is related to the fact that there are very, very special strategies that only exist in quantum mechanics to break ergodicity.
Okay.
But there is nothing special from the perspective of symmetry breaking or time translation symmetry breaking that makes time crystals at all quantum mechanical. There's nothing quantum mechanical about them from that perspective.
I see. Okay. Yeah, thank you.
Another super good question. Actually, yeah, this is really great. Please keep asking questions. So we've changed the context. In 2012, Frank was thinking about, as Kiseoka and Ryo said, the breaking of continuous time translation symmetries, but that's not possible. So the more modern setting in 2015, 16, 17 is asking the question in a periodically driven system. And the question in that periodically driven system is, you have a classical or quantum or quantum many-particle system, and we can ask ourselves whether or not that system, which is periodically driven, whether that system has observables that exhibit a subharmonic response, which is that oscillations at some fraction of the original driving frequency. Much like in the previous slide, where you might have thought, oh, well, that feels really weird. It felt like a perpetual motion machine. Here, I think you have the opposite reaction, which is that, oscillations, even subharmonic oscillations, are basically everywhere. So what's special about this notion? And we haven't gotten that many questions on this particular topic yet, but one of the classic things that happens whenever I give time crystal talks is people ask, Norm, why isn't blank phenomenon a time crystal? And I hope I will be able to answer this in the next couple of slides. So my claim is that now we have to be a little bit more careful. So we think about, as I mentioned, we're thinking about asking about time crystals as a bona fide phase of matter. And of course, the very first slide I introduced was that, again, spontaneous symmetry breaking is kind of the connection to this phase of matter. And so we can ask ourselves a very simple question is, when is it proper or is it allowed to think about a discrete time translation symmetry breaking, just like we explained in the previous slide, as leading to a discrete time crystal phase of matter? So here, this is perhaps a very, very condensed matter viewpoint, but at least, I'll outline specifically what the rules of the game are. So usually when we think about a phase of matter, we have a number of ingredients. The first one is that there should exist a well-defined thermodynamic limit. Just like Ryo was asking, we usually don't think about, a single particle as being a well-defined possibility for a phase of matter. So we usually want to imagine that there exists some set of local degrees of freedom, and there's an update rule, for example, dynamics, that arise from interactions that couple nearest neighbors or suitably local neighbors in these degrees of freedom. In some sense, the sort of classic stat mech idea that there's a well-defined thermodynamic limit. Then, of course, what we've just been talking about for the last slide for a time crystal is that we want there to be a discrete time translation symmetry breaking, that there exists a set of states such that there exists a local observable O, which has periodic oscillations that are some fraction of the driving frequency that persist out to, in principle, infinite times. Classic notion of symmetry breaking. And the last is something that isn't often stated, but is very, very important, is that we'd like the phase of matter to be rigid in the usual condensed matter sense. That the behavior associated with this symmetry breaking is robust to small, locality-preserving perturbations of both the initial state as well as the dynamical update rule. So we'd want the physics of this discrete time translation symmetry breaking to not be fine-tuned. You don't want it to be such that there is a measure zero set of initial states that you have to start in to be able to see the phenomenon, or that no matter how small you perturb the Hamiltonian, that you automatically move away from this time crystal behavior. And that's also very, very standard, that we'd like for there to be some rigidity to perturbations of both the state and the initial condition. So it turns out that even with these rules of the game, in some broad sense, time crystals have been known for an extremely long period of time. So again, zoom out for just 1 second, because I know the audience is broad. Originally, the question was thinking about continuous time translation symmetry breaking. Then we went to discrete time translation symmetry breaking in a periodically driven system. And then we said, but now, in addition to that discrete time translation symmetry, we'd like for there to be a thermodynamic limit. So the physics must be many locally interacting particles. And we also want there to be rigidity. Okay, so again, we've sort of zoomed in a little bit further on the nature of the question. But again, it turns out, even with those caveats in mind, it turns out, strictly speaking, with those definitions, there has been time crystals from many, many years ago. And the specific example that I want to talk about here is something called the logistic map. I think many of you are probably extremely familiar with this. The logistic map has a classic, diction or a nomenclature associated with it, which is that oftentimes you learn about the logistic map having or exhibiting a so-called period doubled route to chaos. I apologize for the coughing. It's sort of trying to get over a cold. But essentially, the logistic map is a dynamical system which is captured by an iterative map. So it usually describes a single degree of freedom x, where the update rule phi, think about this as, for example, a Hamiltonian update rule, simply takes x to rx times 1 minus x. And it turns out that for an appropriate choice of this value r, there absolutely exists a finite volume of initial states, initial values of x, which exhibit period doubled oscillations between two different fixed points. Okay, so I want to be very clear. Why does this satisfy almost every single definition that you want for a time crystal, despite the fact that it's utterly trivial? So here I'm showing the allowed states for x as a function of r for this logistic map. And you can see for lots and lots of different values of r, there exist essentially two different states of x. So the transition rule is apply phi every time, right? You apply phi, 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 phi. So each of those you can think about, for example, as a discrete time step taking time period t. But now, under that application of phi, which is period t, the initial state, which is x, goes over here and comes back, goes over here, comes back, goes over here, comes back. So the observable, which is the value of the initial value of x, only comes back to itself every 2 times that you apply phi. At least at the naive outlook, that looks exactly like what you want for a time crystal, an utterly trivial version of a time crystal, right? And it also has many, many, many different values of r, so it's rigid in that sense. And it also has a finite volume of initial states where this behaves like this. You might say that, okay, this is kind of scary. It seems like this very simple example already satisfies the notion of a time crystal. It almost satisfies the notion of a time crystal, except for the fact that, so it definitely has this discrete breaking of this time translation symmetry. It also is rigid in the sense that there are lots of values of x and lots of values of r, which exhibit this behavior. But it maybe looks like, well, okay, good. We're still safe because there's no well-defined thermodynamic limit. It's a map on a single degree of freedom x, and we usually don't think about single degrees of freedom as phases matter. But it turns out that's not enough. There's actually very, very nice work dating back, decades, where people were thinking about coupled map lattices or coupled lattice maps, where just imagine all you do is you now have a bunch of x's, for example, in a one-dimensional chain that are coupled to each other, and now you apply this phi on all of them. It turns out, somewhat unsurprisingly, that you will also find the same type of subharmonic behavior in these 1D coupled map lattices that are based on the logistic map. So in that sense, I'm sort of pouring a little bit of cold water on the whole field to start off when I'm making the statement. In fact, stable, rigid, many body discrete time translation symmetry has been known for a long time. So if that's true, why is the field of time crystals interesting at all? And this is where we really have to be very careful about the question that we ask. So I really want to emphasize this as perhaps the most important point. There are so many phenomena that you can think about. I don't know, the rotation of the earth, the beating of a heart, biological systems, synchronization, all of these things look like they can exhibit subharmonic oscillations. But my claim is that really the moral of the story is that the difficulty of getting a discrete time translation symmetry breaking very much depends on the class of dynamical system that you look at. Okay, let me say that one more time. How non-trivial and interesting it is to ask the question of, is there a time crystal, fundamentally depends on the class of the dynamical system that you think about. And just to be a little bit more clear about what I mean by the fact that there are different classes of dynamical systems, let me give some examples. So, for example, if you were thinking about isolated many particle systems interacting via classical mechanics, you can have a classical Hamiltonian where we think about the Poisson bracket as the way that we do time evolution. That's one dynamical class. The similar closed system quantum dynamics, you can think about the unitary time evolution as being another class that describes closed system quantum evolution. If you think about open system classical dynamics, so this is a little bit, slightly different from the dissipation that Rio was referring to earlier, but really now dissipation. So think about this classical system coupled to a bath. Then if it's coupled to a bath at finite temperature, and that finite temperature bath satisfies the fluctuation dissipation theorem, then the dynamics are given by Langevin dynamics. And similarly, if you take the quantum unitary closed system evolution and you apply finite temperature bath to that, then usually we describe that by a quantum Lindbladian dynamics. So these are what I mean by saying that there are different dynamical classes. Each of these is described by a set of equations of motion that fundamentally takes a different form. So if you just think about classical Hamiltonian dynamics, the dynamics satisfy that phase space obeys Liouville's theorem. And in some sense, for each of these different classes, the dynamics are measure preserving in some sense that's analogous to Liouville's theorem. But it turns out, for example, that the logistic map that we're considering cannot be written as an equation of motion for any of these classes. It cannot be written as Hamiltonian evolution, no matter how hard you try to write down a Hamiltonian. And in particular, the logistic map is not a dynamical class that is measure preserving. If you think about the logistic map and you take some finite volume of phase space, the logistic map always contracts this finite volume of phase space to a single point. So in dynamical systems literature, we typically call the logistic map a contractive dynamical system. Again, what that means is very simple. In phase space, think PQ. Classical Hamiltonian dynamics have Liouville's theorem. The area of phase space is conserved. The logistic map looks nothing like Hamiltonian dynamics in the sense that it's contractive. A finite area or volume in phase space always contracts in finite time to a single point. In some sense, this logistic map can be thought about as a situation where there essentially is dissipation, like, essentially, coupling to a bath, but no noise. So it's essentially if you, for example, were coupling some dynamical system to a zero temperature bath and you were constantly dissipating out entropy. Okay, so it turns out that in that logistic map setting, or in any setting where you have contractive dynamics, trivial to find a time crystal. It's extremely easy to find subharmonic oscillations for a given equation of motion that essentially satisfies all of the definitions we want. But it turns out that the case of these four cases, which in some sense is a very physical setting, so thinking about either closed many-body classical dynamics, closed many-body quantum dynamics, or the finite temperature version of each of those respectively, It's much, much, much more subtle to ask about the possibility of a discrete time translation symmetry breaking in these dynamical systems. And that, in some sense, is where the modern literature is focused. Are there any questions?
So what's the measure that's preserving in the Langevin? So am I right that, for example, in the quantum Lindbladian, the measure that's preserving is the trace of rho, the density operator? And what about Langevin dynamics? I'm a little bit confused about what you mean by
it's hard to explain exactly what I mean by measure preserving. It's right. In some sense, what I mean by that is that even Langevin dynamics can be evolved backwards in time. So in some sense, there is no real information loss in that sense. But the real sense of what I mean by Langevin and Lindbladian, which is why I put this measure preserving quotes, is that there isn't really a measure. What I mean by that is just that it satisfies fluctuation dissipation. For dissipation, you have to have fluctuations, and it satisfies the standard FD relationship.
I see. So whenever you put in friction, you just have to put in some noise.
Have to put in some noise. Exactly. If you allow yourself to put in friction without noise.
But in quantum setting, the quantum noise is always like is large. I mean, it should be comparable to the strength of the measurement. So the friction that you get in quantum setting has to be comparable. But in classical settings, can't you make the noise to be very, very small compared to how much friction you get? Like,
no, not if you want to satisfy fluctuation dissipation. So
okay.
in classical, you can make the friction. I mean, I guess one thing to say is that you can make the friction very small, but then you'll have a very small amount of noise. So if the friction is small, then the dissipation is small and the noise is also small. But if the friction is large, which is what you really want to do to sort of damp out stuff, then you also have large noise.
So but that's only in equilibrium, no? I thought if you have like a non-equilibrium bath, then can't you make the noise to be?
Yeah, I want that. So the fact that I'm talking about temperature means I'm in equilibrium. Statistical mechanics works.
Okay.
Yeah, I want I mean, it's for an intrinsically non-equilibrium system, I don't even know how to define the Gibbs state very well. So
right.
When I say temperature, that the bath is in thermal equilibrium and temperature is well defined.
So your claim is that the Langevin dynamics, which in equilibrium, but you're driving. So you prepare a state in equilibrium, which obeys the Langevin dynamics, and you are driving this system with external drive.
That's right. So you can still have exactly. So the equations of motion that you write down are Langevin equations of motion, where there absolutely can be a driving term. For example, things can be parametrically driven, but at the end of the day, the friction term is related to the noise term by the classic, kind of like, temperature by the size of the temperature. So the, autocorrelation function that corresponds to the dissipation is scaled with respect to friction by the value of the temperature.
Okay, I see. Thank you. And there's a question from the audience. Saint Pop, would you?
Yeah. For me, so far I understand it. The periodic driving system is usually known as block state. Use that but block state may not be satisfied three conditions of like well-defined thermodynamic limit or discrete time and rigidity. But which conditions that block state cannot satisfy? And can you explain the difference between block state and the time crystal?
I have to say I'm not 100% sure I understood the question. Can you? So I understood that there was like a statement about like block states, for example, when you have, I guess, spatial translation symmetry, and of course, flow K is similar in time. There are there's the flow K block theorem. So can you restate the question one more time, saying I didn't understand it? I'm sorry.
Block state is when there is a time time periodic potential, the states become blocked states. But which use that to be a time crystal, it should satisfy three conditions. But
Yeah.
which conditions does blocked state does not satisfy? Is blocked state equal to time crystal?
So let's be super careful. Okay, let me try to unpack the question a little bit, and then and you tell me if I'm answering your question. So by definition, if you have a periodically driven Hamiltonian, right, that system is called a flow case system.
Yeah, right.
So let's think quantum mechanically for just 1 second. Okay, think quantum mechanically for just 1 second. So if you think quantum mechanically, what describes a flow case system? Essentially, the object that corresponds to sort of talking about the time evolution is the unitary evolution over one period of time. Right? So
yeah,
just super clear, right? So you have a, it could be classical, let's say quantum Hamiltonian, and it's periodic in time. And we're interested, for example, in time period T, 2T, 3T, which we want to very, very clear. So the object that describes the evolution across one period is the unitary of the time-ordered exponential of the Hamiltonian. Do we agree?
So you said it is the time period.
So I wish I could write. I mean, if we were at the blackboard, I could write for you. But so all I'm saying is that from one period to the next. So let me see if I can. 1 second. Let me see if I can try to write a little bit. Okay, let me try for just 1 second. Okay. So you have a Hamiltonian, for example, right? And the Hamiltonian is a function of time. Usually, if you had a Hamiltonian that was independent, what would you think about? You'd think about diagonalizing this Hamiltonian and looking at eigenstates, right? Eigenstates, right? But if you have a Hamiltonian that's a function of time and it's periodic, then the thing that's very natural is to think about basically the unitary that takes me across one full period. So this is the unitary that drives me from time 0 to a period capital T. Okay. I think what you're asking about is this. I think you're asking, for example, that if you now look at the eigenstates of this unitary, these are called flow K eigenstates of this unitary. These are called flow K eigenstates. And you can ask yourself, for example, do these flow K eigenstates essentially sometimes look like time crystals? The answer is yes. The problem is that you cannot prepare these eigenstates in the setting where it's very, very important, actually. So in the setting, let me see if I can find my, where's my, the point is that actually, if you go look at these eigenstates in the setting where you have a time crystal, the flow K eigenstates are essentially macroscopic cat states. And because they're cat states, you actually cannot prepare them. So they basically look like something like, okay, let me see if I can draw, like, all down, like, for example, if you had n spins, oh, this is terrible. Sorry, let's try to, yeah, sorry, it's a little bit tough to draw on this, but the basic point is that, let me see if I can kill this piece now. Sorry, give me 1 second. Let me see, there we go. Okay, there we go. Okay, so let me maybe hide this again. So the basic setting is just, very, very simple, that actually the flow K eigenstates do indeed look like states that if you were able to prepare a flow K eigenstate, it would absolutely, in certain settings, look like a time crystal. But the basic statement is that those flow K eigenstates, just like most of the eigenstates that you're familiar with, are extremely hard to prepare. And the statement is actually that for any initial state that you do prepare, that you're able to prepare, with a finite depth circuit, essentially that will always basically exhibit, these sort of, non-trivial oscillations.
But what if I can make a steady block state?
Yeah, if you can make flow K eigenstates, then even for a system that is essentially a time crystal, it will not look like a time crystal. Right. So, I mean, the point is that the eigenstates themselves, like the way to think about it at some level is that, the flow K eigenstates themselves, what ends up happening is that, they have some pairing in energy such that if you have an initial state that basically is some superposition of them, they basically go in phase and out of phase with respect to each other. So that initial state looks like it basically has oscillations, but the flow K eigenstate itself will not look like it has oscillations. Is that clear, Sane?
Maybe I don't understand you're saying, but
okay.
yeah,
I think,
maybe we should keep going.
Saying, I think, you please consider more about it.
Yeah. Sorry.
Okay, sounds good. So yes, I mean, it's a good question. I mean, I'm happy to chat with you more afterwards, Sane. But okay, so at this stage, basically, I want to be very specific. We're now, mentioning that, in addition to all of the caveats that I said before about when the question is interesting, the most important caveat is that we have to be specific about the class of dynamical systems that we're asking about time crystals in, and only some of them is the answer difficult. Good. So we can ask ourselves, okay, so at this point, why, is it that in the modern, times that we're starting to think about these types of periodically driven phases of matter? I mean, people have known about flow K theorem and flow K block states, as Sane has been saying, for a very, very long period of time. Okay. And so I think it's always really important, whenever there's some new field, you should, very logically ask yourself the question, why is it that people are thinking about this new field and asking this question now? It turns out that the answer is very, very simple. That in a very generic case, if you think about, for example, the first two settings that I mentioned, closed Hamiltonian dynamics of a many-particle classical system, or closed Hamiltonian dynamics of a unitary quantum system, if you think about either of those settings and you add in periodic driving, the basic intuition for what happens is extremely simple. If you take a bunch of interacting particles and you periodically shake them, then eventually these particles should absorb energy from the driving field, and they should slowly heat to a featureless state. So in some very, very truthful sense, the reason why people did not ask this question is for many years, they thought that the answer was always it's trivial. If you have a closed system that's being periodically shaken, you're doing work on the system, so the system must absorb energy from the work that you're doing on it. So no matter what happens, at some late enough time, you always imagine the system is simply going to heat up. More generally, this notion of flow K heating, which is heating of a closed system from a periodic drive, is an example of ergodicity. It's exactly what Rio was emphasizing at the very beginning of the talk. Essentially, ergodicity is just the generic expectation that many particle systems reach thermal equilibrium. But it turns out that for a periodically driven system, the only allowed thermal equilibrium at late times is infinite temperature, because the system is just continuously absorbing heat. So in some very, very deep sense, my feeling on the field is that the interest in time crystals and in periodically driven phases of matter has nothing really to do with time translation symmetry breaking. But really, it's a question about how you can break and if you can break ergodicity in a many-body system. And my claim is that if you ever find a generic way to break ergodicity in an interacting many-particle system, there will be a way essentially in that system to get something that looks like time crystals. Okay, is the obstruction clear? Great.
Yes.
Yep, please. So it turns out that there are many, many different ways to break, and probably more likely to slow down the onset of ergodicity. And we'll go through a couple of these examples, but each of these examples of a different strategy for either breaking or delaying ergodicity corresponds to, for example, a different version of a time crystal. So these days, people call time crystals oftentimes discrete time crystals as opposed to continuous time crystals. So we'll go through these in a little bit of detail, but there are many body localized based strategies that utilize disorder. There are pre-thermal strategies that utilize high driving frequencies. There essentially are dissipatively stabilized things that use explicit external baths. And there's this example of contractive dynamics, which was very trivial, corresponding to the case of the logistic map. But in some sense, in each of these different settings for breaking and delaying ergodicity, there's kind of always a way to get time translation symmetry. So it's the ergodicity breaking that's really the challenging piece of the physics. So let me explain a couple of examples of ergodicity breaking. And already the mantra that I mentioned is already at the top here. Where there is ergodicity, there will be time crystals. So in the quantum setting, it turns out there is a strategy that goes under the name of many-body localization, which I'm sure many of you have heard about, which is the idea that it may be possible to utilize disorder to induce a phenomenon known as many-body localization. And if the system becomes many-body localized, essentially that many-body localization can prevent the system from heating up and absorbing energy from the driving field. I should emphasize already at the outset, the existence of many-body localization is not analytically proven, and certainly the existence of many-body localization in periodically driven systems is not analytically proven. So there are arguments for it, there are arguments against it, and there may be some small system-sized numerical evidence for it, but the jury is certainly far from being out as to the existence of many-body localization. There were two very, very nice works coming out around the same time, experiments from the end of last year. Tim Timiniau's group at Delft and the Google Quantum AI group were basically looking at examples of what would be time crystalline behavior that essentially is stabilized by a finite size version of many-body localization. Another strategy, which is not an infinite time strategy, so the lifetime of the time crystal does not fundamentally diverge as you take the thermodynamic limit, is a strategy that's known as pre-thermalization. And the idea here is extremely simple. If you have, for example, a frequency of your periodic driving, this is like 2 pi divided by the period of the drive. If the frequency of the periodic driving is large compared to the local energy scale of the system, then it turns out that the lifetime of the time crystal can be exponentially long in the frequency over the drive. It's not strictly infinite as you take a thermodynamic limit because there is no system size dependence, but essentially it's parametrically exponentially long in some energy scale omega over j. So for purpose of experiments, it's very hard to distinguish kind of the lifetime of a pre-thermal time crystal from a many-body localized time crystal. And here, it's a very nice way to answer Rio's question. As we'll see in the next slide, pre-thermalization is a strategy that works in both quantum systems and classical systems. But MBL, as far as we understand, is a strategy that's unique to quantum systems. So in some sense, the specialness of sort of, the reason why people talk about, quantum time crystals, it's really a misnomer, in my opinion, coming from the fact that people initially studied quantum time crystals, which were stabilized by many-body localization. And many-body localization as a phenomenology is a quantum phenomenon. But if you imagine, for example, thinking about time crystals stabilized by other phenomenon, and you don't force yourself to require e to the L divergence of the lifetime, then certainly that from just the perspective of time translation symmetry, I don't think there's anything special about quantum mechanics. And of course, another strategy that one can imagine using is dissipation, sort of really extrinsic dissipation. So we are worried in the previous slide, the fundamental obstruction to having phases of matter in periodically driven systems is Floquet heating, is that the system will ultimately thermalize under the ergodic hypothesis, but that because of the heating, that thermalization is to an infinite temperature state. At an infinite temperature, there is no symmetry breaking of any form. So you might imagine, well, what if I somehow just couple the system to a bath? I couple the system with friction, and now I dissipate and allow for that friction to essentially take away the heat that's being inputted by the drive. It's very, very subtle. because even though there's friction, the bath also has noise on the system because of fluctuation dissipation. And you need somehow that noise does not mess up the order parameter, does not lead to lots of domain walls between the time crystal. And so it's not at all a priori clear that if you add in, for example, noise, that you fundamentally will be able to survive the additional, the additional fluctuation that you get. Okay, so it turns out there's lots of work, there's beautiful review articles on the quantum case. But I think the question that I think is kind of fun is to ask about the question classically. So we're really going to ask about classical time crystals. And here I'll introduce two kind of recent works that I think are kind of nice, and they give a sharper picture about the possibility of classical time crystals. So the question we're going to think about is asking about now a periodically driven many-body classical system in some finite dimension, could be 1D, 2D, 3D. And we're going to ask about whether or not it can escape Floquet heating in some simple way. And again, we can imagine looking at the three strategies that we had before. We said that many-body localization is essentially out. We said that pre-thermalization is in. There are very, very nice examples of pre-thermal time crystals that are classical. And so the question that we're going to ask today is, if you think about Hamiltonian plus Langevin dynamics, is it possible that in the dissipative case, we can get a time crystal with a lifetime that diverges exponentially with the system size? Of course, the caveat and the question is that we're fighting the fact that whenever you have friction, which helps you, you also have fluctuations. So we are thinking essentially about the classical Langevin dynamics case. This is the class of dynamical systems that we're thinking about asking for the question of time crystals. Good. So in this second half of the talk, I'll sort of break down the talk into two different strategies. The first part is just going to be the simplest strategy that you often take as a physicist. Try a generic system and see if it works. Cold water, it will not work. And the second part is to be very, very clever and to utilize an analogy to cellular automata. And there's a very pretty result there. So part one, we're going to think about here the parametric resonance of coupled pendulum. And as I mentioned already, it turns out that we will find this is not quite a time crystal, but that nonetheless, along the way, we will find a pretty interesting non-equilibrium phase transition. So what's the setting? It's a very, very simple setting, but yet there's still some interesting answers. So we imagine a set of nonlinear oscillators represented by pendulums in one dimension. The pendulums are coupled ferromagnetically via this cosine qi minus qj term. And it turns out, in addition to the kinetic energy, there's also a potential energy, and that system is being driven. It's being driven parametrically with a driving frequency that's omega d and a driving amplitude that's given by delta. And we're asking the very simple question, is it possible that a period 2, a period double time crystal can emerge in this particular system? In particular, we'd like to check whether or not this can emerge under the specific case of Langevin dynamics. So we imagine, for example, that there is a force on the system where there is, as Ryu mentioned, dissipation from some term that looks essentially like friction, but there's also finite temperature in the presence of noise. So as the autocorrelation function, there's a stochastic force, but that stochastic force is perfectly related to the strength of the friction by the temperature. So turns out, let's go back many, many years to the 1800s, almost 200 years ago, and think about the case of one parametrically driven pendulum. It's essentially the zero-dimensional case, and that already has a very, very long history. At zero temperature, this is not, the situation that we want to think about, because zero temperature is friction but no noise, but just for the setting to be clear at some point. At zero temperature, there exists a very well-known phenomenon. For example, these are Mathieu tongues over here, that you can indeed have the parametrically driven pendulum exhibit a period doubled subharmonic response, where the pendulum can exhibit oscillations at some fraction of the driving frequency. So for example, in blue, we're plotting the trajectory of the pendulum. And for example, it only comes back to itself every 2 driving periods. So if you, for example, took a stroboscopic view and you measured the location of the pendulum every single period, it would be at left, right, left, right, left, right, red, blue, red, blue, red, blue. But since we know we're going to be thinking about a period double time crystal, just for the purposes of the remaining slides, I'll always emphasize that we're only going to look at an even stroboscopic view. Okay, so that will be that whenever you see pictures that look like solid colors, those are time crystals. But it turns out that, for example, if you tune the ratio of the damping to the driving amplitude, so the ratio of the friction to the driving amplitude for your parametric drive, let's call that ratio lambda, clearly there are lots of regimes in this phase diagram where the pendulum no longer oscillates at any reasonable frequency, and you're too damped, and you basically find that the pendulum's oscillations just damp down to 0. Still satisfies fluctuation dissipation, but the damping is just too strong. In that case, what it looks like is essentially that it's no longer blue or red, because blue is to the left, red is to the right. It basically just settles down to being at 0, and there it looks like white. So solid blue or solid red, time crystal, period double time crystal, solid white, no time crystal. So it turns out that for one pendulum, exactly 1 degree of freedom, if you have any finite temperature, what were these very, very sharp boundaries in these Mathieu tongues, they always blur into crossovers. And this is very, very much in some agreement with this notion that 0-dimensional systems cannot exhibit any sharp transition at fine temperature. So this intuition here is now exactly related to Ryu's, intuition regarding Merman-Wagner, okay? But not related to the way Haruki and Masaki Yoshikawa sort of prove their no-go theorem. So I want to be very, very clear here. So let's try to introduce a very, very simple diagnosis of the period doubling. Q is the position of the pendulum. It's driven at frequency omega d, and let's say that it responds at frequency omega q. If you take the derivative with respect to q dot, then you'll get omega q out in front. And you can compute the difference between omega q minus the driving frequency divided by 2. If this is 0, that means that the pendulum is responding at half the frequency of the drive. It's a time crystal. If it's not, then it's not a time crystal. So this is typically in the literature what people call the velocity order parameter, but essentially it's just for these parametric resonances, some order parameter that tells you whether or not you have a subharmonic response. And what you find here is, as promised, that for low values of lambda, V is very, very close to being equal to 0. And so you have a regime where it looks basically period doubled. But as you increase lambda at finite temperature, you see that there's a very smooth crossover. There's no sharp jump of a phase transition, nothing happens. There's just some crossover between this period doubled regime and this no period doubled regime. So let's ask ourselves what happens now for a 1-dimensional system. It turns out at 0 temperature, the answer is that it's almost exactly the same as the single pendulum, as the 0D system, that there is sharp transitions between regimes of period doubling and no period doubling. At finite temperature, you can ask a very good question. If you have, for example, low values of lambda or high values of lambda, this is the amount of dissipation that you have in the system relative to the driving amplitude. You can see that for low values of lambda, it looks totally like a time crystal. For high values of lambda, it looks like the time crystal totally melts into a non-time crystal. It turns out in equilibrium, in 1D from Merman-Wagner, at finite temperature, you cannot have any sharp transition in a 1-dimensional system. So we can ask ourselves, well, is there something interesting for this particular system? Is there a sharp transition for the time crystal to non-time crystal phase, the period doubled to non-period doubled phase in this scenario? And it turns out that at high temperatures, the answer is that it looks almost identical to the 0-dimensional case. It looks like there's a very, very smooth crossover. But as you go to low temperatures, it looks like we see hysteresis. So as we sweep lambda up and then back down, it looks like we see a hysteresis loop. And as we do the sweep slower and slower in time, it looks like the hysteresis loop closes until at some point there is a sharp first order phase transition between the period doubled regime and the no period doubled regime. It looks like there might be a sharp phase boundary emerging at low temperatures. And again, this is strictly not allowed in thermodynamic equilibrium. Goes again back to Ryu's question. All of Ryu's questions have been very good. So in some sense, this is not an equilibrium system. We have a finite temperature bath. So in some sense, that is, a notion of equilibrium, but you're periodically driving the equations of motion. So it's truly a non-equilibrium system. So we can ask ourselves, okay, well, let's really check. Let's really see, is this an actual phase transition or not? If you went, zoomed in lambda, would you see, for example, something that still is continuous, but just is very sharp? So what we can do is we can set up some very nice experiments, numerical experiments that were proposed to us initially by David Hughes, where we, for example, sit in a parameter regime of lambda that, for example, starts off in the phase that is a non-time crystal. And we start off preparing the system with a domain wall where half the system is in the time crystal phase and half the system is not. And then we let time evolve down. And you can see that in this trivial phase, the non-time crystal always eats the time crystal. You can do the same thing in the time crystal phase, and you find that the time crystal always wins. And very, very, very close to the transition, you find that they compete, as you would expect for metastability at first order phase transitions, for very, very, very long times. And you can see indeed that when you look in and you zoom in on the putative transition region, lambda is now much, much, much more zoomed in than the previous plot. It really looks like there is a very, very sharp phase transition. So in some sense, what we think is happening is that there's a phase diagram that essentially does not look so different than the water phase diagram. That there is a parameter lambda, like pressure, and a parameter temperature, like temperature, such that at low temperatures, if you force yourself to cross through a parameter regime like this, you will find essentially that there is a first order phase transition, but at high temperatures, there's only a crossover, which means that there is some smooth path to combine, to move from the time crystal to non-time crystal phase, meaning that there is no sharp distinction between the two phases. There is no sharp order parameter that is strictly zero in the thermodynamic limit. It turns out the easiest way to see that there's no sharp limit is that the time crystal, the period doubled oscillations in this phase do not depend on e to the L. They do not scale to infinite times in the thermodynamic limit. They are fundamentally bounded by some Arrhenius law. So they can be exponentially long as a function of 1 over the temperature. So it can be very long as temperature gets cold, but it's not e to the L in the same way that you would want for a truly thermodynamic time crystal.
Question.
Okay.
So is this critical point depend on the size of the system? Because I have thought that there would be always a transition, coming back to your first slide where you were talking about the symmetry breaking, and I would have thought that this does have discrete time translational breaking. So why would you get?
We would like that, but it doesn't. So in the same sense, in space, you can imagine that there's a correlation line. So think about, for example, a magnet. So, you could have a magnet, and if the correlation line is exponentially large in some parameter, it's a big magnet, but it's still not an actual truly long-range ordered magnet. So here the statement is that it is period doubled. It has something that looks like time translation symmetry breaking for very long time scales, but it does not diverge as e to the L.
I see. And then did you check that this point more or less doesn't move when you change the system size?
Yes, that we've certainly checked, but this point is very interesting. I mean, this point has cost me a lot of lost sleep. So I mean, I would love to have a theory for this transition. Presumably, if you think about, things that you're used to from like, classical physics, oftentimes like a first order line ends at a second order critical point or a tricritical point, or something interesting. And I've been very interested in what if it really is that you have a line of first order phase transitions that ends at a second order critical point. I would love to be able to write down the critical theory for this point, but I don't know how to do it.
So then maybe another question is like, do you have some understanding why these kind of like this order is more robust than the usual Ising? Like, why is it harder to why is it harder to flip the domains in this periodic doubling case than the Ising? Do you have any?
Think about this? Yeah, let me think about it. So it's a good question. Okay, let me think about this for a second, right? So what Ryu is asking is that in equilibrium, for example, if you think about a discrete Ising symmetry, at finite temperatures in 1D for nearest neighbor interactions, you cannot have finite temperature order. And in some sense here, it is actually the same. You don't have finite temperature order because, it is only an exponentially long-lived lifetime. But it seems like, for example, the lifetime of the time crystal is extremely large. I guess the statement is actually that if you go, so I think it's probably this. Think about, in 1D, temperature as a function of like transverse field. So if you lower the temperature very, very low, at zero temperature, you can absolutely have an Ising ferromagnet. And if you lower the temperature very, very low, the size of that domain, the correlation length also gets very, very large. So in that sense, I think, it's not so different from that in terms of its stability. But, strictly speaking here, you just don't have kind of this first order phase transition, but the stability of this is not much more stable than a very large domain Ising ferromagnet.
I see.
But I don't have a very good answer as to why, I don't have a very good answer as to why this type of a system has, a non-equilibrium phase transition, whereas the other system, you just don't have a phase transition ever.
Yes, so maybe another quick related question is that like this kind of is in a similar spirit to what Kaneko have done, right? Despite the fact that you have noise and he doesn't. So my question is, do you know what would happen in Kaneko's setting if they add noise to that model?
We've been emailing with Kaneko about this. I think it's probably the same. I mean, I think I would guess that they'll come to the same answer. But we haven't done it, so we're not exactly sure, but I think that the answer should be the same. That would be my guess.
Okay. Thank you. I see. Interesting.
Yeah. Okay, so it seems like at this stage, at least in this non-equilibrium setting, we have not, we don't have a true phase transition, or we don't have a true time crystal in the sense of timescales. Automatically, when you take L to infinity, the timescale diverges to infinity. So we can ask the question, is it possible to be a little bit more clever? I mean, we took a really simple version of a Hamiltonian. We were thinking about coupled parametrically driven pendulums. Is it possible to change the Hamiltonian a little bit, but in a very clever way to get a true time crystal? But to still stick within the dynamical class of this Hamiltonian plus Langevin dynamics. Before I answer that question, I want to...
One question.
Yes, please.
In the previous page, can you construct, although you mentioned symmetry breaking in Landau-Ginzburg theory, to me, it's still uncomfortable because I cannot find any explicit from the corresponding free energy, whatever you call, some functional in terms of Landau-Ginzburg type, in terms of order parameter, velocity, U. So can you have some standard framework? We know how to derive Landau-Ginzburg theory from, very well-defined step.
Yeah, it's a very good question. Okay, so let me think about it for a second. I understand the question. Let me restate the question just to be super clear. So, usually for standard Landau-Ginzburg theory, or thinking about like an Ising phase transition, you can think about, the free energy. And
yes,
if you have finite temperatures, there may be, for example, a domain that flips. and that, domain, but that domain basically makes the free energy unhappy. So subsequent sort of fluctuations want to make that domain smaller, and that's why you're stable, right? And I think the question that Kisok is asking is basically, is there a similar picture for the time crystal? So is there some similar picture where you can think, if you did make a domain for the time crystal, so something that was like up, down, up, down, up, down, and then a domain down, up, down, up, down, up, what exactly is the corresponding free energy that's essentially getting minimized or serving as the penalty, as the Landau-Ginzburg penalty for sort of not allowing that fluctuation to happen? Let me think about it for 1 second. Just let me think about it for 1 second.
So usually, usually we know in microscopic degree of freedom, we have some composite with other parameter which breaks symmetry and integrate out microscopic degree of freedom, then obtain some, then that's the procedure. So here you have some saddle points in Schrödinger calculus, whatever, you have a saddle point solution. So then, and some other parameter, I don't know,
Yes, okay. So
may I have a comment?
Yeah, please.
All this kind of thing depends on the degree of freedom that you are looking at, right? Observable, which is all the parameter. So you should have essentially projective dynamics. That projects Hamiltonian dynamics onto pure degree of freedom, so that you can have dissipation and others. So this will the answer what Kisok has questioned. So do you understand what I'm saying?
I think you're not. Yeah, exactly. So let me say it a different way. I think that's right. But let me try to say it a different way. But that's right. So okay, or maybe this is what you're saying. But let me try. So essentially, when you have this periodic driving, there's a couple of different settings. So, this setting that we're looking at now is sort of, not maybe the easiest setting to think about it. But I think, I don't know who was asking the question or who was just making the statement about projective dynamics, but I kind of agree, which is that maybe an easier setting to answer the question in, which is not exactly the setting that I'm working in now, but it'll be easy to answer the question, is think about large frequency. Okay. In large frequency, essentially what happens is that at large frequencies, which was this pre-thermal strategy for a time crystal, at large frequencies, you can effectively think about the fact that there is an effective Hamiltonian. So, I mean, you have a periodically driven Hamiltonian, but you can essentially think about expanding the time dynamics or projecting the time dynamics, expanding in orders of 1 over omega. So if the frequency is the largest energy scale in the problem, you can expand in orders of 1 over omega. This is typically called the Floquet-Magnus expansion. And you can expand in orders of 1 over omega. And in some sense, and you'll basically, in order by order, in order of 1 over omega, you will have essentially some Hamiltonian that's basically a time averaged version of the Hamiltonian that is an effective Hamiltonian. At least for the pre-thermal case, that pre-thermal time crystal, precisely the stability of it is the same. It's the same Landau-Ginzburg free energy with respect to the effective Hamiltonian. Whether or not that effective Hamiltonian converges as a statement about the expansion is very hard to say. So the claim in the MBL case is that it really does converge as you take infinite orders. The claim in the pre-thermal case is that it does not converge. And precisely when it does not converge is when basically your system starts to heat up. So I think, always in some sense, in each of these contexts, I think, I apologize, I didn't get the name of who was just saying. I think it's correct to almost always think about there being some emergent symmetry, and that emergent symmetry is something like a Z2, like an Ising symmetry, And the breaking of that Ising symmetry is important for being in the time crystal phase. Does that agree? Whoever was saying the projective case, does that agree with what you were saying?
Well, a little bit, but what I'm saying is, well, what is the projection operator for that kind of projection dynamics? For example, to project a few degree of freedom or single order parameter, something like that. Or it could involve some certain time average.
Yeah, exactly. So again,
okay.
I still don't know about the word project. I mean, project, I'm somehow a little bit
Well,
wary.
for example, in statistical physics, you have a famous projection operator formalism to derive generalized Langevin equation from the Hamiltonian dynamics. Just like a Morin-Swansik. Well, if you don't know, well, I cannot say any further, but this is fundamental to derive this pure variable from the fundamental microscopic dynamics, where the time irreversibility and the the fraction dissipation theorem are derived. Well, well, maybe it's out of focus, perhaps.
No, I think I'm not sure. I mean, I want to be precise. So I certainly don't know that background as well as you do, but I think that the time averaging is important. I think in some sense, like the time averaging is sort of what I'm saying with respect to thinking about these types of expansions, and then there being an effective Hamiltonian. But at least for me, you know, I'm not necessarily thinking about sort of coarse graining in any way. Like I don't want to go from like a microscopic degree of freedom and then think about, you know, for example, coarse graining to a field and thinking about the expectation value of that field. I just want us to work with microscopic degrees of freedom. So I want to think about, for classical spins, a chain of classical spins. For quantum spins, I want to think about a chain of quantum spins. And then when I say, you know, I'm measuring some operator or some order parameter, I'm literally looking at the expectation value of a local operator in that, you know, 1D system, for example. So I'm not sure whether or not, you know, this projection is exactly what I'm thinking about, but I certainly agree that I think that maybe the answer to Kisyuk's question, which I'm not 100% sure, is that essentially one way to think about this for some of the different types of time crystals is you should think about, on average in time, there is an effective Hamiltonian that describes the physics, and the effective Hamiltonian sort of, you know, the effective Hamiltonian is time independent, and the free energy penalty associated with that Hamiltonian is essentially what stabilizes the, you know, unhappiness of forming, you know, domain walls.
Can I comment?
I see. Thank you. Yeah.
Just talk about it.
Can I comment?
Of
So, in my point of view, I was thinking of this, you know, free energy in non-equivalent setup as, can we think of it in the L-Nils law perspective, meaning that, like, in the free energy language, there's a probability of going from, you know, this state to this state, larger than the other way around. And you can think of that without free energy, just purely dynamically. You have this state, like a two metastable state, but with noise, it can transfer from one to the other. But one is more stable than the other in the sense that, you know, one can transfer with a higher probability than the other. I think that will like translate in some sense to the free energy without going really back to the free energy.
But I have to admit that I'm not sure I understand the words you're saying. And in principle, if that were true, I think that would be nice, but I'm not sure that's true. Like, I'm actually not sure that if you think about it from or another way to say this, I think that maybe it is true, but that it's true because at the average Hamiltonian, there is a free energy that makes that probability of having a domain wall small. I still think that, you know, like you could say, like, you know, so I mean, I think what you're saying, Rio, is like, okay, you know, forget the free energy, you know, maybe there's just some reason basically why, if you have a state that is a good time crystal and you make a domain wall in the state, that sort of, you know, the probability to go back to that state is better than the probability of going this way. And my answer is that yes, that's probably true, but I think it comes from the, you know, free energy penalty that you get from the average Hamiltonian.
I see what you're saying. Yeah, okay. But the reason, the precise reason is not clear, right?
Yeah, I mean, I'm not sure. I think is the correct answer. Perhaps, I suspect that people know, but I'm not 100% sure. But I would venture a guess that basically, at least for the cases that I'm sort of familiar with, like if you think about the pre-thermal regime, that it's the, effectively, you almost always, there has to effectively be the breaking of some emergent symmetry. And in the pre-thermal case, that emergent symmetry is an Ising symmetry. It's like the magnetic, it's like ferromagnetism. And there, I think I'm 100% sure that the stability is basically based on the free energy of the average Hamiltonian. But for like MBL, I'm not so sure how to think about it.
Okay, thank you.
Good, super, super great discussions. Okay, so the question now is, can we change the rules for the equations of motion and get to a system where it's still classical, where classical Langevin dynamics leads to a lifetime that diverges as e to the system size? And to answer this question, I'm going to start by introducing a slightly different idea, which is an aside. And in particular, I'm going to introduce a totally different dynamical class, which is not physics at all. It's maybe a little bit more computer sciencey. So again, I emphasize in the beginning that I'm interested in these four dynamical classes: Hamiltonian, unitary, Langevin, Limbladian. But now I'm, contradicting myself. But I want you to think about, a different class of dynamical systems that are related to cellular automata. So it's not physics, but I claim if you ask the question and you give yourself the leeway to ask the question, that time crystals trivially exist in any in any cellular automata system in any dimension d greater than 0. So again, not a physical setting, but still an interesting question. Okay, so what is a cellular automata? You are all, I'm sure, very familiar with cellular automata from classes that you've taken. It's just some rule, some update rule, for example, for how exactly, a cell, for example, in this case, a binary bit 0 or 1 changes its state based on its history, right? So it turns out that at some level, I mean, I'm not going to leave physics forever. We will come back to Langevin dynamics, but there's a very, very intuitive connection between Langevin dynamics, which are an example of a continuous time Markov process. And in some sense, a cellular automata is a discrete time Markov process. There is a probability distribution on the sites sigma I. These are each of the individual sites sigma, for example, can be plus or minus 1. At a given time, there's an update rule, and then you get updated to the distribution at time t plus 1. Langevin dynamics are almost the same. You're thinking about a probability distribution of phase space at a given point in time, and you have a differential equation that tells you how that probability distribution evolves in time. But of course, Langevin dynamics are slightly different because you have noise. So it turns out that the analogy between Langevin dynamics and cellular automata should really be something called a probabilistic cellular automata. That's the P in front of the CA, where in fact, your transition rule is not deterministic, but it's a deterministic transition rule plus some random set of errors, which you should think about as fluctuations in your Langevin equation. It turns out that if we now restrict our attention to PCAs, that ergodicity is well known to be allowed to be broken in PCAs. So PCAs are well known to support ergodicity breaking without any fine tuning. I think one of the first results from this was from Andre Thum in the 1970s or so, or maybe even before that. He introduced a two-dimensional cellular automata that was called the northeast center model. So for every single cell can be either red or blue. And the update rule for a cell is to look at itself, its northern neighbor, and its eastern neighbor, to do a majority vote on these three sites, and then to transition to the majority vote answer. And you do this for every single site, and that's how you evolve. It turns out that Thum was able to prove that this particular cellular automata has two stable distributions, obviously all red and all blue, without any need for any symmetries. The amazing thing, this might feel very much like a ferromagnet to you. There's all down and all up. These are two stable distributions at finite temperature. But Tomb's model is much, much stronger than two-dimensional finite temperature ferromagnetism. Tomb's model is stable to biased noise. So in a ferromagnet, if you had some small probability that spin down flips to spin up more often than spin up flips to spin down, you're dead. There's only one distribution, it's all up. But Tomb's PCA is freaking remarkable. If you have that red flips to blue more likely than blue flips to red, it doesn't matter. It's still, by some small amount, it still has that there are two stable distributions without, even in the presence of biased noise. And of course, the presence of these two stable distributions is an example of ergodicity breaking. It turns out that Peter Gotch, much later, more than 30 years later, proved that there's also a cellular automata in 1D that does the same thing. That is two stable distributions without the need for any symmetry, and that is indeed stable to biased noise. So, okay, I'm just going to show a very, very simple model video that I coded up in BASIC of the dynamics here. So you can see, here, if you have, for example, an island, a minority island, under the Tomb rule, which is the deterministic version of the Tomb rule, no PCA, it just gets corrected. Essentially, what Tomb has figured out is a PCA that implements error correction. So you can go to the next slide. So immediately it turns out that you can imagine that the simplest version of a PCA that is a time crystal is apply Tomb's rule followed by flipping every single state. What do the dynamics look like? Well, just look like this. The minority island still gets corrected, right? That's very key. So you might have thought that, oh, well, now that you flipped it, in the next step, the island should get bigger, but it doesn't matter because it turns out that you're basically error correcting. So the majority always error corrects the minority. And even when you flip back and forth, it always does that error correction. And this means that if you keep letting this go, this is absolutely a time crystal. The rule is apply NEC followed by spin flip. It's the same rule every period, but the system only comes back to itself every 2 periods. So now you can also say, okay, let's look, for example, at a situation where we have the same dynamics, but now for a PCA. I'm just simulating a cellular automata, but the PCA is now biased, okay? I have a PCA that is biased noise, has lots of random spin flips, and you'll see that now there's stochastic spin flips, there's more purples that always appear than yellows, but every single time it just gets corrected. This is essentially Tomb's rule in action. So again, it's not really physics because we're talking about a very specific dynamical system, which is a cellular automata. Trivially, a cellular automata cannot obviously be represented as a Hamiltonian anyway. So it turns out, but if you allow yourself to ask about cellular automata, PCAs, because they exhibit very, very good ergodicity breaking, immediately allow for exponentially long-lived time crystals that are independent of the initial state. Good. So now you can say, well, okay, so we can certainly believe now that for a PCA, I haven't done anything. I've taken results from Tomb and just made a statement about time crystals in those results. But we'd like to go back to our Hamiltonian setting, to the setting of the 4 classes of actual physics dynamics that we're often interested in. And you can ask yourself, can you accurately simulate a probabilistic stellar automata with a Hamiltonian plus a Langevin equation? It turns out this is a very classic question in mathematical physics. Can you embed a discrete time Markov process in a continuous time Markov chain? It's called the embedding problem. There's many, decades of research on this embedding problem. And I think there's no generic answer to the embedding problem, but I think the answer is that for this particular rule, there is a very, very simple way to embed from this PCA into a Hamiltonian or a Langevin-based simulation of it. Okay, I won't go into the details, but essentially you sort of, double the degrees of freedom, and you use one set of degrees of freedom as a memory for the other set as you do the time evolution. And it turns out we can simulate the PCA, that's not physics, it's just simulating the cellular automata itself. And we can simulate the PCA and look at the order parameter that corresponds to the magnetization. And there we see a very nice phase transition. And then we can literally write down a Floquet-Langevin simulation of what we think the PCA should be doing. And we find that, and we cannot prove that it simulates the PCA perfectly accurately, but at least for increasing potential depth, it looks like it simulates the PCA quite well. An open question that's very non-trivial is whether the noise from the Floquet-Langevin dynamics satisfies the error rules that are implicitly assumed in Andre Toom's paper. We can't prove it. We've done a lot of work trying to show numerically that it does, and as far as we can tell, it does, but it's a very hard thing to prove. That would be very cool if one could make progress on it. Okay, so let me, I really sincerely apologize. I realize I've gone over by a long time. But just as a very quick outlook, so, there's a question that I think is very interesting, which is this version of a time crystal essentially related to a pre-thermal time crystal where the bath dissipates heat from the pre-thermal time crystal? I don't know, but it seems like there's some very, very big distinctions between the dissipative version of the simulation of a PCA from a pre-thermal plus bath time crystal, but I think it's a very interesting question to consider. And more broadly, let me end with just 2 slides. There's still a lot of active questions and open questions in the broad field. But I think that, there's certain people, that really emphasize, there's only one time crystal. It's the quantum MBL time crystal. But I don't really subscribe to that opinion. I think that the question of time translation symmetry breaking can be asked in many, many different settings with many, many different interesting results. So for open stochastic systems at finite temperature, we've talked about basically kind of like essentially time crystal order that persists for an exponential 1 over temperature. We've talked about error-corrected versions of breaking ergodicity. For closed systems, there are classical and quantum answers that relate to pre-thermalization. There are intrinsically quantum versions that are related to many-body localization. And there's also classical answers that are fundamentally related to the Kolmogorov-Arnold-Molzer theorem, where the stability of few-body systems in terms of actually breaking ergodicity. So I think that depending on whether or not one's interested in closed and deterministic systems or open stochastic systems, the nature of what protects a time crystal can be extremely different. Let me just end, I've worked with lots of people through the years on time crystals. I should absolutely give credit to one of my best friends in life and in physics, Mike Zalatel. We spend a lot of time doing physics and eating dumplings together. My student, Francisco Machado, is now a postdoc at Harvard. Chintao, who was a postdoc at the time, is actually now faculty, currently at University of Arizona, but actually moving to California. And Chetan Nayak and Leon Balance are long-term collaborators on the classical time crystal side. And let me also thank you for your attention.
Yeah, thank you very much for the very stimulating and very also pathological talk. So we already have quite a few questions during the talk, but are there any more questions?
Can I ask one side question?
Please.
First, thanks so much. The nice talk. Can we study phonon or polaron in time crystal? Can you give some comment for that, if it's possible?
Yeah, I mean, I think you can, but I don't know that it's necessarily related to time crystals. So in some sense, like, if you think about, asking about phonons or, what the phonon spectrum looks like, and asking about, long wavelength excitations, for example, of the degrees of freedom, I think it's fair to ask about that, but I don't really know, whether or not, the spectrum of the phonons or the nature of the phonons is, I don't necessarily see how exactly that couples to the time crystalline order in a very simple way. But you can certainly ask in a time crystal about, what the low energy spectrum of the excitations look like if you think about, starting from some ordered state of an effective Hamiltonian, but I'm not sure whether that really couples directly to the time translation symmetry breaking in a distinct way.
I see. Thank you.
Yeah, thank you.
So any other question? So I think you mentioned that the breaking the ergodicity is the kind of the point. Then my naive question might be that like there's, I think one of the prototypical example of ergodicity breaking is spin glasses. Do you think that those spin glass systems can exhibit this kind of discrete time crystal? I mean, do you know why haven't many people consider about that? Like, given that manipulated localization, does the work, then why do you have any idea why?
So I think you're exactly right. So I was just going to say, in some sense, I think about many body localization as a spin glass, but it happens to be a spin glass that basically, maybe if it exists, persists throughout the entire spectrum of the Hamiltonian and isn't just, related to low energy states. But I think in some sense, if, we have, it's complicated. I think, the spin glass literature itself is kind of non-trivial. But if we believe that, for example, a spin glass does bake ergodicity for, below a certain temperature, below a certain critical temperature, where you enter the spin glass state, and that ergodicity, is broken out to exponentially long timescales and system size, I think that's just as valid a way to basically stabilize the time crystal as MBL.
Because, like the MBL, I think the very clear difference between MBL and spin glass is that you have a classical counterpart in spin glasses. There's, classical spin glass exists while classical many-body localization probably doesn't, right? So I thought that's quite a big difference.
Yeah, that's right. Although I don't know how to think about this, I guess, yeah, so in classical spin glasses, I guess, is it proven, I guess, for you? I don't know. Is it proven that the lifetime of the glasses state is exponential in system size?
I think probably somebody might correct me if I'm wrong, but I think in the Anderson model in the lower critical dimension is considered to be between 2 and 3D. And so like, at least in numerics, it seems that there is a critical temperature in 3D, but not in 2D. As far as I see, but I'm not a spin glass expert, so maybe a spin glass expert in the audience might correct me.
Yeah, but I guess my broad answer is that if, I guess I knew that there were some questions. I don't know if they're fully resolved. That's useful to know. But I guess my general statement that if you have, a classical or a quantum spin glass that breaks ergodicity below some TC, will be perfectly fine for a time crystal.
I see. Thank you. So any other questions? Okay, if not, let's thank the Norman again.
Thank you very much.